Okay, Quiz 12.1, intermolecular forces and liquid properties. So let's look at this first question. State the strongest intermolecular force for each of the compounds below. What we're going to look for is whether this molecule is nonpolar or polar, and whether it's capable of engaging in hydrogen bonding. So CH2O, that's a formaldehyde molecule. It has a Lewis structure like this. So it is a polar molecule, polarized toward that oxygen, but it is incapable of hydrogen bonding. And so this will have dipole-dipole as its strongest possible intermolecular forces. COOH, this is formic acid. Oops. Should be HCOOH. How about that? I made a bit of a mistake there. This has a hydrogen attached to an oxygen, and it's got oxygens with lone pairs all over the place, and so formic acid is able to engage in hydrogen bonds. Carbon dioxide is a linear molecule. It has polar bonds, but those polar bonds are oriented directly opposite each other. So overall it's a non-polar molecule. That means that dispersion forces are the only type of intermolecular force that carbon dioxide will exhibit. C6H14, carbon-hydrogen bonds are nonpolar, and that's the only thing we have here. Well, and carbon-carbon bonds, which are also nonpolar. And so that will also have only dispersion forces. So C6H14 is dispersion. Then we'll have CH2Cl2. And this will be polarized toward the chlorines, so this will have dipole-dipole. And then finally, CH3OH, that's methanol. Oops, CH3OH, there we are. And it's able to donate to a hydrogen bond. It's able to receive a hydrogen bond with the lone pair on the oxygen. So this is a hydrogen bonding molecule. Okay, so the next one, we're going to be making comparisons between different similar species. So F2 and Cl2, they're both halogens. They both have a perfectly nonpolar bond. So what's the difference? The chlorine is larger. It has more shells of electrons, and so it's more easily polarizable. Chlorine will have the stronger intermolecular force. Then looking at C3H8 versus C12H26. Again, the size matters. The C12H26 has 4 times as many carbons. It's much larger. It will have stronger intermolecular forces. Then the straight chain C8H18 versus branched C8H18. Here the shape matters. The straight chain will present a larger surface area, and it will therefore have stronger intermolecular forces. The straight chain wins there. Okay, can you provide an explanation for why liquids exhibit surface tension? And you may find it useful to draw a diagram. So, surface tension seems like a property that is exhibited by a bulk liquid, like a droplet of water, which contains billions and billions and billions of individual water molecules, but surface tension actually arises from molecular interactions. So I will draw here a diagram that shows the molecules that make up the surface layer versus molecules that make up the bulk. If I pick a molecule on the surface, then it has, I'll write this, surface has fewer neighbors. Okay, and that means that it's experiencing fewer attractive interactions. It's got fewer intermolecular forces with neighbors. Compared to, say, a bulk molecule, that is a molecule that's buried into the middle of the sample. Bulk molecules have many neighbors. And so that means that it has many attractive forces. Attractive forces lower the energy of a system, and so these bulk molecules are lower in energy than the surface molecules. We can state that another way and say that there is an energy cost to having a molecule be on the surface compared to being in the center. And so energetically, you can reduce the energy of a system by reducing the number of molecules at the surface, or in other words, by reducing the surface area. And that is ultimately what is behind the phenomenon we call surface tension. It is an energetic trend toward lower surface area in order to minimize the total system energy. Okay, so this next one I really like. This concept kind of blew my mind. So soap bubbles take a tiny amount of water and stretch it out to form a very thin shell. The shell has both an inner and an outer surface, and so you compare that to a droplet made from the same amount of water, and a bubble will just have this enormous surface area. So based on this information, do you predict that soap increases or decreases the surface tension of water? So you can't make a bubble without soap. What does soap do to make bubbles possible? Well, remember, a high surface tension means that there is a high energetic cost to creating surface area. With a high surface tension, there's no way that you could create a stable bubble, because the energy cost for creating all of that surface area is just too great. So what soap will do is actually reduce the surface tension in order to allow bubbles to form. And when I was just learning this stuff 80 years ago, I thought, I don't know, something along the lines of a bubble has this skin that forms the shell, and it's stable, and so it must be really strong. It's almost like it's got this strong skin that is creating the bubble, and so I would naively thought that soap must increase the surface tension to make like a stronger surface that's able to form that bubble. And the reality is it's the exact opposite. It's a weak surface tension that allows the bubble to form in the first place. Okay, and then lastly, water in a glass vessel will form a concave meniscus. So that means that water will look like this in a capillary, whereas mercury in a glass capillary will form a convex meniscus. So this is what mercury looks like. And this is what water looks like. What can we tell about adhesive and cohesive forces in each case? Well, if you think about it, the meniscus here in the case of water It shows water climbing up the glass. And that means that the adhesive force between water and glass is high. In fact, it's higher than the cohesive force of water to itself. So adhesive is greater than the cohesive. That is why the water climbs up. It is sacrificing attractive interactions to other water molecules in favor of creating more interactions with the glass wall. And then mercury here does the exact opposite. It's like the mercury is trying to get away from the glass. And so here the adhesive forces between mercury and glass are very weak. They're weaker than the cohesive forces of mercury with mercury. And that's it for quiz 12.1.